Part 3, Section 4.2, Mean Value Theorem. We're just going to jump right into this one because the Mean Value Theorem is it's similar to Rolle's Theorem. They're related. Rolle's came out first. It's like version 1.0. The Mean Value Theorem came out later. It's version 2.0. It starts out sounding a lot like Rolle's Theorem. It says, if f is continuous on a closed interval a to b. That's the same as the number one requirement for Rolle's Theorem. And differentiable on an open interval a, b. Well, that's the same as the number 2 requirement for Rolle's Theorem. But then it hops right into the word then. So that third requirement of Rolle's Theorem no longer exists. That is, f of a does not have to be equal to f of b. The left-hand endpoint and the right-hand endpoint don't have to have the same, what's the word I'm looking for? Or the same y value. Yeah. It just jumps in and says there's a unique number c. There exists a number c in a and b such that f prime of c is equal to f of b minus f of a divided by the quantity b minus a. Now, what are they trying to say here? Well, this one is actually a little bit easier to see from a picture. So here I have some function f of x. In this case, this is the function f of x equals 5 minus 4 divided by x. Okay? I have an interval. So the interval a, b here would be 1 to 4. So from 1 to 4. Right? So on this closed interval, our function f is continuous. I can draw it without picking my pen up. It is differentiable on the open interval ab, which is 1 to 4. Now clearly this function has issues at x equals 0, but frankly I don't care because 0 is way over here. And we only care about the interval from 1 to 4. So the fact that this thing has issues, I don't care. All right? So then what we're going to do is we are going to take the 0.11 on the graph, the 0.44 on the graph, draw a line between those. That is going to be a secant line. Remember from way back when, secant lines are just a line that goes through 2 points on a curve. And what mean value theorem says is that the slope of the secant line was going to be matched somewhere on the curve for some point on the curve with the slope of the tangent line. Or that this blue dashed line here, is going to be parallel to the red dashed line there. That the slope of the secant line will be equal to the slope of the tangent line. And how do I say the slope of the secant line is equal to the slope of the tangent line using math language? Well, the slope of the tangent line is f prime at some value c. The slope of the secant line is a y value minus a y value divided by an x value minus an x value. Y sub 2 minus y sub 1 over x sub 2 minus x sub 1. That's just the slope formula, right? But if we fancy that thing up, we can say that the slope is the value of the derivative, and that f of b is just our y2, and that f of a is just our y1, and then b minus a is just the x2 minus the x1. So what does the mean value theorem say? Well, it says if your function is continuous on some closed interval a to b, and the derivative exists for all values on that interval, it's differentiable on that open interval from a to b, then there's going to be at least one number c. Then there exists a number c in that interval where the slope of the tangent line is equal to the slope of the secant line. The slope of the tangent line is equal to the slope of the secant line. So that's what we're looking at here. Right? For this function, the slope of the tangent line at the point 2, 3 is going to be the same as the slope of the secant line going through the points 1, 1, and 4, 4. Right? And what I can do is I can verify that by just using a little bit of calculus. Right? So first off, the first thing I have to check is my function f of x continuous on 1 to 4? And it is. It does have issues at 0. It is discontinuous at 0, but it's good everywhere else. 2, is its derivative. Does its derivative exist on the interval from 1 to 4? Well, I don't know that one yet, so I'm going to go ahead and find the derivative. If this is my function f, what would f prime look like? Let's see. When I'm looking at this, what I'm really seeing is I'm really seeing this. I'm seeing that f of x is 5 minus 4x to the negative 1. And so then the derivative is just going to be positive 4x to the negative 2. Or if you prefer, 4 divided by x squared. Now, clearly, oops, I did what I shouldn't ever do. Clearly, that derivative is going to have an issue. It's going to, again, have another issue at 0, but we don't care. So it's good where we care about. And then mean value theorem says, and this is the then part of it, remember these are the ifs, there exists a c, an element of the interval 1, 2, 4, such that the following is going to be true. F prime of c is going to be equal to f of b minus f of a divided by b minus a. And so if I plug in to this everything that matters, I'm going to get 4 over c squared, and that's the f prime of c from right here, is equal to f of b. Let's see, what's f of b? Oh yeah, that's going to be 5 minus 4 over 4 minus f of a. That's going to be 5 minus 4 over 1 divided by b minus a, 4 minus 1. Now if I do a little bit of cleaning up on the left-hand side, that's just going to stay 4 over c squared. On the right-hand side, that's 4. That's 1, 4 minus 1. So this is equal to, what, 1? And then if I solve that, that gives me that c squared is equal to 4, which means that c is equal to either positive or negative 2. Okay? Now this is kind of what we talked about in in Rolle's theorem. Sometimes the algebra is going to give you answers that aren't answers. Right? Technically, this just gave me 2 answers. It says that c could be negative 2 or c could be positive 2. But I'm just going to ignore this one because what's the interval that we care about? Well, the interval we care about is that 1 to 4, and negative 2 is not on an interval. So then the only value that matters is the MVT. Okay, the solution for MVT is when c is equal to 2. Oh, MVT? Mean value theorem. The solution, or the value of c that satisfies the mean value theorem, is c is equal to 2. Okay? So some people make the argument that we shouldn't even bother with Rolle's theorem because Rolle's theorem is just a special case of the mean value theorem. Because the mean value theorem says that f prime of c is equal to f of b minus f of a. Well, Rolle's theorem said that the numerator, that these 2 values here were the same. And if those 2 values are the same, this just turns into 0 divided by b minus a, which is just 0. So essentially you're just saying that f prime is equal to 0. So you could actually ignore Rolle's theorem, pretend it never existed, hop right into mean value theorem, and you wouldn't miss a thing. Because on the rare case where you actually are working with Rolle's theorem, then your numerator of your mean value theorem, f of b minus f of a, is just going to work out to be 0. Then that fraction is just going to turn into 0, and then you're looking at Rolle's theorem. There's no reason to necessarily do both. All right, so down here, our next example. Find all values c that satisfy the mean value theorem for the function x squared minus x minus 12 on the interval negative 3 to positive 4. All right, now before I even begin to look for values for c, I'm going to make sure I can. So what are the 2 requirements? First requirement is it must be continuous on the interval -3 to +4. So is f continuous on that interval? Yes, f is a polynomial function. Those are continuous for all real numbers, so we're good there. 2, does f prime exist on the open interval -3 to +4? I'm not sure. I'm going to go ahead and find f prime. So what is f prime? Well, derivative of x squared is 2x. Derivative of negative x is -1. Negative 12 is 0, so 2x minus 1. 2x minus 1 does not have any issues, so it will exist on the interval from -3 to +4. I have no worries there. Okay? And so if those two things are true, and we just showed that they were, they're both good, then, the 3 if you will, there must exist a c such that f prime of c will be equal to f of b minus f of a divided by b minus a. Okay? All right, I'm going to do some scratch work over here to the side. What's f of b? Well, f of b is going to be f of 4. F of 4 is going to be 4 squared minus 4 minus 12. 4 squared, 16. 16 minus 4, 0. Okay. And then f of a. F of a is f of -3. That's going to be -3 squared minus 3 minus 12. 9, right? Oh, wait. Minus a -3, so that's actually a +3. So 9 plus 3, that's also 0. Huh, what do you know? You know what we're looking at here? We're looking at using the mean value theorem to prove that Rolle's theorem works. So when c equals 1/2, the mean value theorem is satisfied because the instantaneous rate of change, I'm going to throw a phrase at you here, the instantaneous rate of change is equal to the average rate of change. Okay? The instantaneous rate of change is equal to the average rate of change. All right, find all values c that satisfy the mean value theorem for the function f of x equals 1/x on the interval -2 to +2. All right, so I'm supposed to do the exact same thing I just did up there for mean value theorem, but before I do anything, I'm going to make sure that I can. So is f of x continuous on the interval -2 to +2? Well, f of x is 1/x. 1/x looks like this, right? 1/x has a giant issue when x is equal to 0, which is right in the middle of our interval. And so the answer to that is no. And so the mean, whoa, that was a weird looking M. The mean value theorem does not apply for -2 to 2. Are there other intervals that we could use where 1/x would be a good function for the mean value theorem? Yeah, absolutely. We just can't have any interval where x can be 0. Because x can't be 0, we get division by 0 error, so mean value theorem does not apply. I cannot do this. Again, like with Rolle's theorem, I think they're going to want you to put an NA or something like that, so make sure you read those directions carefully. And that really brings us to the end of this. My entire job here, my entire purpose was just to introduce the Rolle's theorem and the mean value theorem to you guys. We took a look at them. We figured out how they work, when they work. We did 2 examples that did work. And we did 1 example that didn't work, so I'm feeling pretty good about this. I'm going to close this one out. Next section will be section 4.3. Have a great day.